The first half today we will continue on the tutorials. We'll continue on the tutorials, and then after the two tutorials that are scheduled for the day today, we will be starting with the invited talks. Some of them will be virtual, some of them will be physical. And to kick off the day, I would like to invite Dr. Prashant. Dr. Prashant is at Atria University. He works on satellite imaging, and he would be talking to you today about diffusion models. Right? Now, the reason this diffusion models has become important in weather forecasting is because what Bharatan talked about yesterday, which is GraphCast, was one of the first models that came out of Google for using graph neural networks for weather forecasting. And that was a 10-day look-ahead forecast. The one that has come out more recently in the last 2 years, again from Google, is a 15-day look-ahead forecast, and it has been shown to outperform in certain aspects the graph-based algorithm. And this new model from Google is based on diffusion models. So Dr. Prashant would be doing the first half of this session, which is diffusion or introduction to diffusion models. And then a couple of collaborators from UT Austin would be doing the second half of the diffusion models as to how diffusion models are used for weather forecasting. Right? So with that introduction, I would like to invite Dr. Prashant.
Good morning all. Thanks Dr. Praful for a nice introduction. Audible? Okay. The agenda of the discussion is, let me give some introduction to the deep learning basics, the journey, whatever you have traveled yesterday. I will not touch upon too many things, just I will give the journey from deep learning, how you travel to generative models. Then I will talk about few things about the diffusion model, the forward and reverse process. Then I give some demo so that you can understand how diffusion model works. Okay, I will keep it as simple as possible so that you can understand the concept better. In the deep learning discussion you have gone through yesterday, you learned basically you understand the convolution neural network architecture and also some transformers. The basic agenda of understanding this architecture and transformer is to extract features and also the patterns from the given data. That means it is supervised learning. That means how you are going to extract the features and the data from the given. It can be an image or a text or any sensor signal. Okay. The discriminative models are used to classify and also predict based on the given input. For example, object classification or object detection, image classification. Then if I want to predict the temperature, what is the temperature tomorrow, then you can use the discriminative models, which is going to give you the prediction. Then the one important aspect here is the term spatio-temporal systems. The weather is an example of a spatio-temporal system. That means here the geographical location, that is longitude and latitude, plays important role here. Then temporal means it is going to vary with respect to time. If you take weather into consideration, if you take a particular location, then you should know what is the longitude and latitude, and also what is the time we are talking about. That is the meaning of spatio-temporal. If you see the representation here, the weather today, tomorrow and next day. That means here the generative models are the powerful class of models which can predict labels or values to generate the data. The example or the advantage of generative model is it is going to simulate the realistic new samples, which is not possible from the conventional, whatever you learned yesterday, the convolution or whatever. That means here you can generate the new samples like images or videos or even the future weather maps. Okay, how it is going to generate, I will talk about in few minutes. This generative power is very important when you are going to address the application like spatio-temporal systems. The example is weather forecasting, okay, where the futures are uncertain. Nowadays you can see the rainfall is very uncertain, right? Okay, how you are going to model to handle uncertainty? Basically, there are two types of signal. One is deterministic and other is non-deterministic. Deterministic means it can predict before its occurrence, and uncertainty means it is not possible to predict before its occurrence. If it is possible to model what is the uncertainty before its occurrence, then definitely can do good prediction. It can be for example, the rainfall or disaster management, where these find application. And also it is not possible to predict nowadays the uncertainty with a single deterministic value. Then how to handle this? This diagram indicates the usage of generative model to handle spatio-temporal system. That means weather forecasting is a spatio-temporal prediction problem. I told about what is the meaning of spatio-temporal. Prediction means you are going to predict we are going to in future what is the weather tomorrow, what is the weather next 24 hours. I am talking about it is not seasonal though. If it is random, if it is deterministic, definitely it can be a seasonal one. If it is random, it does not depend upon the season. How you are going to model if it is not seasonal one? Then you have to go for generative model to address this particular problem. Then the traditional problems are good, it can be accurate, but it does not scale with high resolution and also the real time needs. Okay. Then the generative model can learn the distribution from the future state. Here the Markov chain plays very important role. In the forward process, the diffusion model, there is a transition from one state to the other state that I will demonstrate later. Then the Markov chain, it depends upon only the previous data. Okay, that means it can learn the distribution of the future state. For example, state 1, state 2, state 3, state n. Then the state 2 is depending upon the state 1. State 3 depends on state 2. State 4 depends upon state 3. That is called as Markov chain. The diffusion models are well suited when you are going for denoising. Okay, the denoising corresponding to the noising is corresponding to addition of noise, that is bringing the amount of uncertainty, that is called as noising. Denoising means elimination or removal of noise. How you are going to remove the noise? In the reverse process. Basically addition of noise in the forward process. I have input data with me, I am going to add noise, I am going to generate one pattern or one, okay. Then I am going to add again the noise which is Gaussian noise. Then I am going to find what is the next pattern. I am going to simulate a sequence of pattern by adding noise for different timestamps. For example, if you want to generate 100 complex structure, then you have to add noise 100 times for different variances. The beauty of the whole diffusion process is for each step you are adding Gaussian noise for different variances. The advantage of having different variances is, for example, here in the first step I am going to take the lower value of the variance, then the uncertainty is minimum. The variance indicates the uncertainty, the spread in the distribution curve. In the second timestamp, I am going to add again the Gaussian noise for a different value of variance. That means I am.
This is for all the input variables or just some particular variable? So we have 4-5 variables.
Exactly.
So the noise, every timestamp we are adding into all the variables?
Yes. So it depends upon what are the parameters you are going to consider.
So we have a backend for each parameter.
Exactly.
We are adding them.
The advantage of the beauty of the diffusion model is we are going to add the Gaussian noise for each timestamp for the different variances. That means you start with a lower value of variance at the end of nth timestamp. If you take 100 as the last timestamp, then you have higher value of the variance. That means you are trying to generate a complex pattern. In the reverse process, you are going to do denoising. That's what gradually denoise. That means in the reverse process, you are going to eliminate noise step by step. Same thing, if you consider 100 timestamps in the forward process, there is 100 timestamp in the reverse process, which is gradually eliminating the noise. And again, for denoising or the reverse process, lot of modeling is available. Okay, but the most of the model uses unit architecture that will be discussed by Dr. Manmeet and Naveen. They will give demonstrate about that one. Now, it provides a natural way to model how clouds form because it is generating a complex pattern which is random in nature. How storms evolve or how temperature spreads. The spreading is because of the Gaussian distribution. All through learning patterns directly from the data. Because I have an input data sample in the beginning, then I am going to add noise for the input data. I have one pattern, again I am going to add noise, next pattern, like this. The diffusion models can learn to simulate a distribution of possible future weather states, allowing to generate multiple realistic scenarios. To give the example, today the weather is quite sunny, right? Then yesterday also it was quite sunny. But if you take the day before also it was quite sunny. If you want to predict what is the weather tomorrow based on these 3 days, the indicator is tomorrow also it is quite sunny, right? But if there is an uncertainty, how you are going to handle? If you take the example of weather, now I am generating a complex pattern. Tomorrow it may be sunny, it may be raining, it may be cloudy. All patterns I am having. Okay, that means it is going to simulate all possible scenarios of the weather. Yeah.
So you are saying that we can, instead of giving a single prediction using these diffusion models, we kind of generate multiple plausible scenarios, right? And that's most of the times we do in the weather forecasting, traditional weather forecasting using physical models as well, where we have ensemble perturbation and then we have sampling of different possible ensemble numbers from the beginning, based on the initial state. So I'm trying to understand like how dependent it will be on the initial state in case of machine learning models like diffusion models. Because you said that at every step, what it does is it removes the noise. So let's consider that in the initial state itself, or the data we are forcing, or training our model on, it has some noise because we are adding it. So if it removes the noise...
The input data is noise you are talking about.
Yeah, so if it removes the noise at each step, how different the solutions will be, how different the individual predictions will be, for example.
That means your input data is noise even.
Yes.
Then you are going to add noise in the first timestamp. That's what your point? Then you are adding again the same...
So let's take an example. For producing a weather forecast, we have different initial conditions, which means you have initial condition X, right? You added some perturbations, which might be random. Let's not go into that. And based on that, your solution diverges, right? And based on that, you have different sort of predictions given by physical models, right? So when you say that in the diffusion models, it gives you multiple realistic scenarios in the similar fashion, how dependent it is on the initial conditions or the data you give as an input?
It has to depend upon the input data only, right? Because in the denoising, you are trying to...
So do you create multiple initial conditions as well? Like do you create multiple input data for training the model?
I am not getting the...
Actually, the process is very simple. For example, image we are giving.
Yes.
So at each level we are adding noise.
We have this ensemble weather forecast.
Then what happened is
We slightly change the initial condition and generate multiple weather runs.
at each level we are
Physical models.
removing that noise.
So we get
During
10 to
this
50
time, the model is
forecasts or
getting
50
fed
forecasts.
for this input.
So maybe
And
here also can we
the
generate such kind of
will have a
probabilistic
different
forecasts.
kind of image.
Yeah, you can create with the different variances.
So on the input
Different variances.
there, right?
So how does it produce ensemble?
So ensemble is enough.
Okay.
Ensemble is enough.
Ensemble is the average value you are talking.
These are those.
It's like a generator discriminator kind of thing.
Yeah, we can discuss.
Denoising is like a discriminator kind.
Yeah, it is unit segmentation, yeah.
So like in the game we have generator discriminator, similar
Correct.
kind of things here. Here also we have a fake image or a live image and then we just
Correct.
distributor is correcting it. So it's like denoising.
Exactly.
The different name which comes there.
I think in the demo you may understand better, I think.
A rainfall usually in a gamma distribution. So you are adding the Gaussian distribution noise. So how does it work?
No, the rainfall is Gaussian distribution I'm talking about. That means uncertainty is there.
It will be in gamma distribution. So are you transforming it to normal distribution? Adding the noise?
No, first see, you have input data with you. I am going to add Gaussian noise to that. Okay, I have one pattern with me.
The input data always we try to make it in the Gaussian distribution before training and before normalization also. So that is even I'm going to tell in my talk. So
Fine. The diffusion model for spatio-temporal dynamics, why it is more suited? It is well suited for because they are learned to generate complex pattern, as I told now, through iterative denoising. In the reverse process, every step we are trying to eliminate noise because that's the advantage here, and capturing both spatial structure and also temporal evolution. Temporal means based on the time. The stepwise generation allows modeling uncertainty over time, making them ideal for forecasting scenario. Okay. Unlike one-shot models, they provide fine-grained control over dynamic processes, especially in systems with inherent noise like weather and climate. Okay, this is a justification for using diffusion models for weather forecasting application. Okay, this will give you the difference between both the model, deterministic model and probabilistic model. Example, diffusion model. Okay, it is quite simple. In deterministic model, it produces a single forecast for the given input, whereas diffusion model generate multiple possible future from the same initial state. Again, I think it has answered your question. Same initial state. Okay, the example is run a physical model, get one future weather state, but whereas in case of diffusion model, you are going to get multiple weather state. The limitation is it does not capture the range of possible scenario. That means the different uncertainty condition. It is not possible to capture in deterministic model. Whereas in case of probabilistic model, it is possible. You can clearly see the multiple scenario, the initial state, and it is the weather. This is the difference between both the deterministic and probabilistic model. The point to be noted here is the discriminative model learns the boundary between the classes like CNN or regression by modeling the condition of probability, focusing on predicting labels from the given data. In case of generative model, it learns the data distribution itself by modeling the input or condition of probability by enabling them to generate new realistic data sample. This is a very important point here. That is going to differentiate the generative model from the discriminative model. The transition involves shifting the focus from classification task to data synthesis. I am generating a new set of data, requiring models that understand the underlying structure of the input space. Okay, I am not going to talk about more on UNet, but I mentioned because in the demo Dr. Manmith is giving, they talk about this UNet architecture. UNet architecture is generally used for image segmentation, actually design, but it is repurposed to in diffusion models to iteratively generate images via denoising steps. Okay. Okay, in the deep learning framework, okay, whatever in the last started discussion, you learned about CNN, RNN, transformer, etc. The difference here is, these two are very important point to note. The hybrid approaches integrate physical laws with deep learning for more reliable prediction. If you can come up with a hybrid approach by combining the physical model with the deep learning concept, then you can go for more reliable prediction. This fusion of AI with atmospheric science is transforming the forecasting, climate research and disaster management. Okay, all these are very uncertain. If you see here, you can start with a clean image, then you are going to add step by step in the forward process. In the reverse process, you are going to do denoising again step by step. Then you are going to create a realistic new image with multiple scenarios. If you want to understand a diffusion model, what are the essential things required? One is you should know the basics, the probability, and what is the meaning of noise injection. Then the evolution means you should know what is Markov chain. Then you should know something about some concept of deep learning. Then you should know what is the meaning of forward and reverse process. Then what is denoising. Then sampling. The mathematics is what is the meaning of training objective, then network, and what is the loss function, then what is the diffusion process. The application is, it has multiple application, image generation, but here the discussion is more on weather prediction, but it has multiple application, image generation, weather forecasting, then drug design, etc. Okay, again it's the same thing, but in a different way it is representing both the forward and reverse process in the diffusion process. The interesting point here is in the forward process you are going to generate data by first destroying. I am talking about very simple sentence, destroying the whole input image because you are going to add noise multiple times. Then at the end of the nth timestamp, definitely you are going to see the noisy version which is completely deviating away from the input image. You are destroying the whole input image and you are going to teach a model how to reverse the destruction. That is the basic one line understanding of the diffusion model. Okay.
In the reverse process, again you are putting random noise. Then again you are going. So initially there is a gradually add noise, pure noise.
They are denoised.
Then denoise. After that denoise there is again random noise. So once you have the denoising sample, again you are putting the.
No, this should be the original, reconstructed actually. This is reconstructed. Once you remove denoising, you are going to get the reconstructed image. That is image generation I am talking about. That is not random, it is a reconstructed image.
Images are changed.
Yeah.
Images are changed. Random noise image comes first, after that denoise.
Correct.
So they separate. One is the correct one is the noise is separated. So
There should be a combination of the noise plus the reconstructed image.
at the output.
Exactly. Okay, this is what the input data is the weather data. The weather data, it can be a temperature, wind, etc. You can clearly see THW. It indicates the number of channels, how many inputs you are feeding. It can be a number of weather variables. Then the timestamp, how many timestamp we want to have to generate the complex pattern. Then what is the height and width or long, that's the input given to the diffusion model. Then the prediction, it can go for future weather prediction, and it is going to do denoising in every stage, and you have multiple timestamp. And the data sources, I will not talk about this, but you can have n number of data sources for capturing the data. Generally for rainfall, I think ERFI is, I am not a weather expert, but ERFI is going to give the input data for this. In the forward process, you are going to add Gaussian noise, which is a multivariable weather step by step, then simulates uncertainty or noise in atmospheric dynamics. In the reverse process, the denoising network, that is unit. Definitely, the simplest way of denoising is use a Gaussian filter, which is a low pass filter, which is going to, it is very simple. I am not talking about unit. Other than the unit, the simplest model you can go for reverse process is you go for a Gaussian filter, which is going to eliminate noise, but the limitation, it is not trained. That's why the reconstruction may not be superior. That's the limitation, but the simplest way of doing denoising is use a Gaussian filter, which is a low pass filter, and noise is a function of high frequency. Okay, again the input image, step 1, step 2, if you see that step number 1000, it is completely deviating from the input image. That's why it's destroying the input image, I told, no? Something like this. Then the noise subtraction, just if you go for a simple subtraction method of eliminating noise, it's not so simple as it looks like, then the output looks like just a simple diagram to indicate it's not so simple as it looks like. Noise subtraction. No, it is not forecasting. It is a simple image generation. There is no forecasting. That's why it is image denoising analogy. It is not nothing to connect with weather forecasting. Okay. Then the application relevance, definitely it is the weather forecasting application here I am talking about. You are taking the input image which is relevant to weather forecasting. Image is here a map of weather variables, temperature, pressure, wind, etc. By training on the past weather data, the diffusion model learns how such maps typically evolve. Again, the weather variable, training on the past data, you are going to create.
That means we can say it is a downward scaling,
Which one?
making high resolution image, clear image, that kind of method.
Yes?
So the input should be only images. This is image to image transformation.
Okay. This one talks about the stochastic differential equation. Why I am talking about this? There are two components here. One is drift and diffusion. Generally, the drift is more predictable, that is deterministic, whereas diffusion is random in nature. Again, the drift is indicates the average prediction or trend change over time. For example, if you want to find the temperature in a particular season, summer or winter, then it is nothing but the drift is shifting over a period of time. For example, in summer the maximum temperature or average temperature can be 35. During rainy season it can be 30, or during winter it can be 25. Those values are going to shift. That talks about the drift actually. The seasonal pattern, the drift indicates the average direction or trend of change over that period of time. Whereas diffusion is very random and unpredictable fluctuation. That is the difference between both drift and diffusion. And both can be modeled as a stochastic differential equation. I will not touch upon this. Okay, this is a representation of the both forward and the reverse process. In the forward process, you are going to add noise. You can clearly see the data, then x1, x2, xt. You are going to add Gaussian noise with zero mean here, zero indicates. Then you are going to generate the data. In the reverse, you are going to do the denoising step by step to obtain the particular output. In the step 0, it's the original clean data. Then from step by step, we are going to add Gaussian noise. That means here, I will show a simple demo here so that okay, this is what the Gaussian I told about, the meaning of the variance. Here the mean value is 0, the variance is increasing, you can see, the spread is increasing. For each step, you can start with this particular addition of the noise, then in the second timestamp this one, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, like this. That means the variance is increasing, that means uncertainty is increasing over a period of time. That is what the timestamp is doing here. Okay. Now, if I shift the mean value, now the mean value is 2. Again, same thing, but for a different variance, for each timestamp I am adding. Now, this is the output. A simple diffusion process. There is no, I am not using any unit architecture here. Simple diffusion process using Gaussian filter. If you see here, this is the, assume this is the input. T equal to 0 means there is no addition of noise. In the timestamp 1, addition of noise, and timestamp 2. You can see the uncertainty is increasing over a period of time. If you take t equal to 10, it is completely deviating away from the input image at t equal to 0. In the reverse process, I am trying to do, but actually this should be same as the given input. But here, since I am using a very primitive technique of using Gaussian filter, where there is no learning involved, I am not training the network. That's why the performance is not up to the mark. That's why they move to unit architecture for doing this. And definitely we will, later Manvij will talk about the unit architecture, all those things in the debate.
So, related to what Vidit sir had asked, so in the end product, very pixelated sort of thing, and then we are adding noise in the forward step. We reach at some point, and from there we go backward, and it looks like the image quality has improved.
Quality?
So basically, the number of pixels has improved because the shape of that particular thing has been cleaned.
No, the pixel will not improve, because if you take the input image of some dimension, the number of pixels remains same thing only. The dimension remains same thing. Okay. The Gaussian filter, it is going to denoise. The dimension of the image will not change.
Okay, it doesn't.
It remains same.
Okay, so it can't do something like downscaling
No,
then.
downscaling, if you want to do, you can do it as a pre-processing.
Okay, got it. That makes sense.
So you said the weather forecast output will be probabilistic one. So how are you defining the uncertainty in terms of standard deviation or like an ensemble numbers? Ensemble as an ensemble number. So usually the deterministic value for a pixel it will give at this location 8 millimeter rainfall.
That is longitude and latitude you are talking about. Okay.
For a pixel, he actually meant the entire this thing as a grid, pixel list. So, probabilistic means you will give either a range of values like maybe 20, 30 and something, or a standard mean and standard deviation. So, what will be the output of this kind of progressive models like mean and standard deviation or
Okay, it depends on the reverse process, which are modeling they are using. There are plenty of models available, but I am not touching upon all those things. Okay, but there are plenty of models available for doing reverse process. It depends upon the application, it depends upon the requirement, it depends upon the complexity. What is the resources you are having? For example, if you want to implement a Gaussian filter for denoising, if you want to implement unit architecture, the complexity is completely correct. It all depends upon the resources we are having. Okay, I think the last slide. Yeah. Any questions? I think I think he will join and he will give the demo and he will talk about that.
Using a Gaussian distribution for adding the noise and removing it, at what level and how much has been added, that is going to be maintained and the resource process also. Other than Gaussian, is there any approach which can be used to add the noise?
Generally, the Gaussian, yeah, the Gaussian distribution is generally it is popular because of its the distribution bell-shaped curve. It is going to simulate the real-time scenario compared to other distribution of noise.
Any other can also provide like that?
I have no idea. Okay, thank you.